Good day and welcome to the first part of our discussion on maximum and minimum values, which is a first step towards one of the big applications of calculus, optimization problems. So the motivation for this topic is this idea of optimization, where a typical optimization problem in some way, shape, or form asks us, can we somehow maximize or minimize some type of quantity? So, for example, you might think in business you might want to maximize profit or minimize cost. And throughout this chapter, we'll explore many such applications. But the starting point for all of these is to kind of lay the groundwork and make sure we understand what we are talking about in terms of what a maximum or minimum value is relative to a function, and also come up with a procedure that involves calculus that we can use to maximize and minimize a function. So the first thing is I just want to look at an example of a function f of x whose graph is sketched in black. And what I want to note is that this function is defined, it looks like, on the interval from a to e. And if we think about the possible outputs of the function, what is the point on this graph that would correspond to the absolute largest output? And hopefully you're looking at it and saying, well, all the way to the right. So in this case, yes, it has an absolute maximum when that input x is equal to e, and we say it has a maximum value that would be the largest possible output of f of e. And that's corresponding to this point on the graph, e comma f of e. And from a similar perspective, if we look at the graph that we see drawn in f, where does the smallest possible output occur? And it looks as though the smallest possible output occurs down in this valley associated with an input of d. So we have an absolute minimum at x equals d, that is where it occurs, with a minimum value f of d. And that's corresponding to a point we have on this curve, d comma f of d. And just to make sure we all understand kind of this intuitive concept of absolute maximums and absolute minimums, let's go ahead and just make that a bit more rigorous. So we would say that a function f with a domain d has an absolute maximum at c, where in this case we're thinking of that c value as being an input, if the function is larger at c than it is anywhere else. Okay? That is to say, if f of c, the function output at c, is bigger than or equal to f of x for all other inputs. So that would be for all x in that domain D. And in this case, we call f of c the maximum value. And a common question we are going to encounter is, for a given function, determine the maximum and minimum values. So similarly, we would say that a function has an absolute minimum at some input x equals c if the function output at c is smaller than every other possible output. So that would be to say f of c is less than or equal to f of x for all x and d. And similarly, as you might have guessed, we now call f of c the minimum value. And the maximum and minimum values of a function are things that we are oftentimes attempting to find, and we actually call these the extreme values of f. So the maximum and minimum values, the biggest and smallest outputs, we refer to those as being the extreme values of the function. And before turning the page, if we shift back up to our graphical motivation, note that even though the maximum value occurs at E, there are also kind of what we might think of as these other extreme type points where it's not the absolute maximum, but at those values, you're certainly bigger than everything around it. And similarly, there's what happens in this valley where it's not an absolute minimum, but you're actually smaller than everything around it. And this is going to lead us into the language of a local maximum and a local minimum. So in this case, we would say that we have local maximums at x equals a, c, and e, where the function at those points has values bigger than everything surrounding it. And intuitively, we see we have local minimums at x equals b and x equals d. So let's now turn the page and go ahead and define these concepts and then investigate an example. So continuing on our discussion, for a given function, it turns out we may not only be interested in absolute maximums and minimums, we might want to somehow restrict the scenario so it's just local maximums or local minimums. So we'll say that a function f has a local maximum at some input c. So once again, we're thinking c is where this occurs. It's the input to the function. If there is an interval that contains c, so c is somewhere between x1 and x2, such that for every input in that interval, f of c is bigger than f of x. And I do want to note there's a very intuitive feel to this. Kind of what we're saying is that f of c is bigger than or equal to f of x whenever x is close to, or we'll say near, c. So locally around c, f of c is the largest possible function output. And note we can define the exact same thing in terms of a local minimum. So we would say that a function f has a local minimum at x equals c if, well, instead of saying f of c is bigger than or equal to, f of c is smaller than everything near it. So hopefully a very kind of intuitive concept, and you can see that graphically if you flip back to the previous page. I do want to note there's kind of a small subtlety. Typically the local maximums and minimums do not occur at an endpoint of the domain. But that's not something we are going to worry about. And by that I mean whenever you are asked to determine local maxes and mins, it's perfectly fine for them to occur at the endpoints of an interval. And with that in mind, let's kind of explore an example that ties this all together. So a very reasonable function that we can all hopefully sketch and visualize is cosine of x. I would like you to pause the video and sketch the graph of cosine on the interval from 0 to 4 pi. And then purely from inspecting that graph, I want you to just tell me what are the local maximums and minimums, what are the absolute maximums and minimums. So pause the video, maybe take 2 to 3 minutes to sketch the graph, determine those local maximums and minimums. So hopefully you spent a few minutes working on this. We have the graph sketched. Note cosine oscillates back and forth indefinitely between plus or minus 1. Cosine of 0 is 1. Cosine of pi is minus 1. And cosine of pi over 2, 3 pi over 2, 5 pi over 2, and so on are all equal to 0. And just looking at this graph, hopefully we can all agree that intuitively we see that we have maximum of values occurring at 0, 2 pi, and 4 pi. And those would be local maximums. At 2 pi, 0, and 4 pi, when you are in this interval from 0 to 4 pi, the outputs there are larger than everything around it. And similarly, if you look at what's happening at pi and 3 pi, those corresponding function outputs are smaller than any inputs around pi and 3 pi. So we would say that we have a local minimum at x equals pi and 3 pi. And if we just think about the behavior of cosine, it's always oscillating between plus and minus 1. The largest it can be is 1, the smallest it can be is minus 1. So it turns out that all of these local maxes, these are also going to be the absolute maxes, and the local minimums are all absolute minimums. And we would say that the absolute maximum value, pick your favorite one of those inputs, is 1, and your absolute minimum value, pick either of those two inputs, pi, say, is minus 1. And this completes the first part of our discussion on maximums and minimum values, which is really just all about laying the groundwork for what's to come. Where we want to go next is somehow determine when can we guarantee a function will have absolute max and mins, and once we are guaranteed that there are absolute max and mins, how do we find them? So stay tuned and take care.